So it is lecture number 15, and here we will talk about the joint probability mass function followed by further consequences of joint probability mass function. That means if you are having joint probability mass function, then further we can define conditional probability mass function and marginal probability mass function. Various things we can define. Just at hand, if you are having joint probability mass function, then we can do various things. Now, reverse what we can do if we are having idea of conditional probability mass function, marginal probability mass function. By mixing those, by composing those, we can what get back our joint probability mass function. So that one is a more computational approach, and it demands for better understanding of multiplication rule in the case of dependency of two random variables. So here we will have two random variable, and we will talk about dependency and independency between two random variables. So those things further will come. That conditioning approach will come here again. So first I would like to go to discuss about outline what are the major content that we will cover in this lecture. So first I will talk about joint probability mass function. I will introduce, and I will also talk about motivation. So simply why we are talking joint probability mass function. Joint word, it might be clear to everyone. It is talking about something what it is, what joint activity of something, two more things, or like if you are having a random experiment. In the random experiment I had already told that you can define various random variables. So if you are defining various random variables in the same experiment, then we can observe the joint activity of any two or more than two random variable in together. So if you try to measure the distribution of joint activity of any two random variable, then you have to come up with one distribution that we are calling it joint probability mass function. So we will talk about that. After that, we will go to discuss about suppose we are having a joint probability mass function, then from there can we go to marginalization? That means marginal probability mass function. Also, marginal, that is simple. If you are having a random variable x, then the corresponding probability distribution or probability mass function of that random variable, we denote it by just a function of x only. So this is what this is. If you talk from joint perspective, that means if you are having more than more two or more than two random variable, then simply if you talk about individual probability mass function of one random variable, then we can say that it is what marginal probability mass function. Marginal probability mass function. Also if you take probability mass function of y, then we will talk that also marginal probability mass function of y. And here we observe x and y both vary jointly. So if you are taking joint probability mass function of x and y in together, that we will denote it by function of two variable. It would be function of two variable, and marginal probability mass function happens to be function of one variable. And likewise, we will have conditional probability mass function. That means if you are having two random variable x and y, then suppose you are observing few value of y first. That means we are having conditional random variable x given for those observed y. That means a condition has been introduced by the observed value of y. So for that perspective, we will introduce another kind of probability mass function, that would be what conditional perspective. So we will define like this way: x given y. That means we are observing y, few value of y first. So here we will have another probability mass function that we will call it probability conditional probability mass function. Remember that conditioning is coming from the some value of y, observed value of y, and hence we can say that this conditional probability mass function, it would be just function of x only. So you can simply say that it would be function of x, because y you have already observed. So that means if you, what is meaning of observed value? That means that one is certain to you. You don't have to worry about that y. Y is not varying. You have already observed, so you have already seen y. So that's why only this conditional probability mass function would be just function of x. Similarly, if you suppose someone is observing x first, so for that person, we will have conditional probability mass function like this one: x y given x. That means x is observing first. So here it would be function of y for fixed x, that x you have already observed. So it would be function of what? Just y. So this kind of probability mass function we will see it here. So that means it is function of y. All these are part of today's lecture. Yes, any question? Who is that person that's saying that bifurcate the probability mass in this class? Because everything is in record. Okay. Actually, this one is message. Someone is, I think, trying to log in using a different mail, and I won't allow because I told that just use institute mail in order to log in. So someone is trying to log in with different that personal Gmail. Don't try to do that. The institute mail is good in various perspective because later I will assign various assignment and other things. And here in the Google Drive, it is just institute mail is providing G Suite. So in G Suite, you will see the various functionality of what we call it. That G drive and other things, collab, and many functions you will see it here, and also a space that you will get in G drive. That one is, I think, around 1 TB, something like that. Very large space you will get. So take benefit of that institute mail in order to maximize the capacity of G Suite. I don't try to come up with your personal Gmail, and that would be not good because that one is having limited facility. That personal Gmail happens to be very much what personalized and limited facility. You can't go for major application of G Suite. So my suggestion: don't try to log in with personal Gmail. Just use Institute Gmail. Institute Mail, that one is also provided by Gmail, and it is paid version. That's why you are getting maximum benefit. Now we are going further to discuss about uh, joint probability mass function. So till now, whether slide is visible or not? Is it visible? Anyone respond? Okay. So I'm here to discuss about joint probability mass function or joint discrete random variable. So joint discrete, if we are having a joint discrete random variable, then we will talk about the distribution by joint probability mass function. That means in the same experiment, we are having more than two or more than two random variable, x, y, z, various random variable. We can define it, and we can talk about joint occurrence of those things. So coming to joint probability mass function, first I will talk about motivation. So in probabilistic model often involves several random variables of interest associated with the same experiment. Remember that this word is very important, that when we are talking about joint probability mass function, then we will take those joint random variable from the same experiment. It is not like that one random variable is coming from one experiment, another one is coming from other experiment. That situation is not here. The one experiment we have to be come up with, it must be prefixed. For example, in a medical diagnostic, the diagnostic, what you see, the result of several tests may be significant. Like someone is trying to some doctor is trying to infer that one particular patient is having some particular kind of disease, then that doctor will suggest various tests. It is not like that only one test would be sufficient to infer about that particular disease. It is not like that. So that person will go for various tests. So each test will what signify, it will go to one random variable. So based on those joint occurrence of those random variable or joint occurrence of those random things, random events, that will leads to our inference of the particular disease. Or similarly, if you are in networking context, then the workload of several gateway may be of interest. So various gateway would be there to provide a smooth network, a smooth communication of anything what you want to communicate. So this motivates us to consider probabilities involving simultaneously the numerical values of several random variables and to investigate their mutual coupling, how they couple together. So that thing, so the coupling, we will measure it through joint probability mass function. So here I will define here. Consider we are having two random variable x and y, and both are associated with the same experiment. Then the joint probability mass function we can define by the corresponding joint probability. So joint probability I had already discussed in elementary class, elementary probability in model 1. So same joint probability mass function we will define for any two random variable xy, we will define like this way, that it is a function of xy, it is function of two variable. In such a way it is defined by that it is equal to property that x is taking, first random variable x is taking value x, and second random variable y is taking value y jointly. It is joint here. The comma sign is talking about joint occurrence or end. In a logical way you can say that end, or in a set theoric way you can say that intersection. So both coming together, coming simply both coming together. You can't leave one and go with one the other like that. So both are occurring together. So for every pair of numerical value x and y, for x for random variable x and y for random variable y. Yes, any question? Someone is asking any question? Anyone is having any question? No. Am I audible or not? Okay, fine. So I will go further to describe more about joint probability mass function. So this joint probability mass function, it determines the probability of an event that can be specified in term of the random variable x and y, such as we, that means we can define joint event for joint activity of x and y by introducing certain properties, that A is the set of all pair which satisfy certain property. Certain property, it will come from the problem. What problem we will have, from there we can come up with a one property that will be satisfied by jointly both random variable x and y, and in that case we can calculate the property of, yes. No, I will take example here. So for example is all about here that we are taking a four-sided dice and we are rolling two times. So in that process, how many outcome we will have? We will have 16 outcome. 4 into 4, 16 outcome. Okay, and two tuple, how many in number? 16. 16 to I, each outcome would be characterized by ij, where I is talking about outcome of the first role and j is talking about associated with second role. Okay, so here I is the result of the first role and j is the result of second role. So this outcome can be arranged in two-dimensional grid because we are taking two times. So that means one that outcome of the first role, we can say that it is defining a random variable x, and outcome of the second role, that is defining a new random, another random variable y, but both are associated with what uh, this experiment, that rolling a dice twice. So here x will take what are the value, possible value x will take? X will take 1 2 3 4. That means first phase, second phase, third phase, fourth phase. And y will also take four value: 1 2 3 4. Okay, these are the possible value y will take. Okay, now we are going further. We will define here, somehow we can calculate the joint probability mass function of this experiment of these two random variable, and it is tabulated here. You can see that. Now I'm talking about marginalization, how we can marginalize to get marginal probability mass function. So that means here the marginalization is coming in two perspective. One is summing here x, that random variable talking about outcome or outcome or result of the first role, that one is taking along horizontal axis and y is taking along vertical axis. Y value is taking along vertical axis. So what you do, if you marginalize with respect to x, that means you do horizontal sum. You are summing horizontal sum. So you can observe like this way. So if you do sum of this one with respect to x, take x here, uh, like if you do horizontal sum like this way, uh, this horizontal sum is sum all these joint probability. So these are each probability in the entry, what these are, we are calling it joint probability. Total 16 in number. You will see that these joint probability for each there are 16 outcomes, so that's why we are getting 16 joint probabilities. Okay, now we are summing horizontally. So if you sum this, what we are getting 3 by 20. If you sum second row, we are getting 7 by 20. If you sum third row, we are getting 7 by 20. If you sum fourth row, we are getting 3 by 20. So if I talk about this marginalization, we did marginalization with respect to x because we are summing with respect to x. X is varying along row or horizontally it is varying. So in that process we are getting a distribution of y. This one is here vertically y is varying. So for y equal to 1, we are getting this probability. If y equal to 2, we are getting this probability. If y equal to 3, we are getting this probability. And for y equal to 4, we are getting this probability. So we can say that what does it talk about? It is talking about marginal probability mass function of y. Likewise, if you do sum along column sum, that means vertical sum, like sum all these probability along the vertical. So if you sum, you will get this in the first column it will sum to 3 by 20. In the second column, that will sum to 6 by 20. In the third column, that will sum to 8 by 20. In the fourth column, it will sum to 3 by 20. And what does it is talking about, if you observe here, x is varying, so it is talking about distribution of x, and hence we can say that this one is what marginal probability mass function of x. So if once simply I would like to say that if you are having joint probability mass function, somehow you came to know, then easily you can find marginal probability mass function from the joint probability mass function. So that technique I will talk later, how to calculate joint probability mass function of in an experiment, that I will talk. So we need to understand, in order to calculate joint probability mass function, we need to understand what is conditional probability mass function. So I will talk about this, and after that I will take few example where you can easily calculate joint probability mass function with the help of multiplication rule. So coming to define conditional probability mass function, I will talk a few more things that I will take a few more example, like in later I will define conditional probability mass function. So there is one problem I am taking it here. So again it will talk about joint occurrence of various random variable. Okay, and here that then we, if we know the joint occurrence of various random variable, then how we can calculate related thing like mean, expectation, variance kind of thing. So suppose in a probability class there are 300 students, and each student has probability 1/3 of getting grade A. Getting grade A, that one is independent of any other student. That means it is not like that other student is helping in order to get grade A. So it is totally independent. So we can see that a binary situation for each student. So that means with probability 1/3 that a student will get grade A, and with probability 2/3 that a student will not get grade A. So that is the binary situation I would like to say. So right now take it like binary situation. Now question is coming that we have to find the expected number of the student that get grade A. Expected number of the student that grade in those get A. How many student out of 300 student, how many student got grade A? So that we have to find. That is the question. So in order to formulate this, we have to introduce first that binary situation that we best model by Bernoulli random variable. So we are defining a Bernoulli random variable like this way. Let us define xi equal to 1 if ith student gets grade A, otherwise xi is taking 0. Look, if you pick any ith student, then that ith student will either get grade A or will not get grade A. So the binary situation is there. So with respect to ith student, we are defining a random variable xi. So definitely this xi is what? It is a Bernoulli random variable, and all how many suppose n number of students are there, n number of students simply, and n equal to 300. Sample size is you can say that it is 300, n equal to 300. So we are defining n number of Bernoulli random variable, and each one is having uh, common expectation. I had told that if you are defining a Bernoulli random variable, and if you are finding the expectation of a Bernoulli random variable, what is that? If you are defining a Bernoulli random variable, the expectation would be what? Uh, it is taking two value. One is 0, 0 with probability, 0 with probability. What is the probability of getting the none getting grade which is not A? That probability would be 2/3. So it will 0 into 2/3 plus, and what is the probability of getting uh, grade A? That one is 1/3. That means 1 into 1/3. So and hence we can say that expectation of xi is 1/3. Here you can observe that expectation is 1/3, and if you are willing to calculate variance, variance I had told that variance is what? Product of for a Bernoulli random variable, variance is product of probability of success into probability of failure. A probability of failure would be what? 1 minus p. So that means probability of success is 1/3, and probability of failure is what? 1 minus 1/3. That one is 2/3. In total, if you simplify it, what it would be 2/9. So variance of each xi is 2/9, and expectation of each xi is 1/3. So that you come up from the problem. Now after that we are defining a sum of these random variables. Simply you can say that it is this x is a function of these n number of Bernoulli random variable, and it is sum, and each xi happens to be independent of xj. So independency. So due to that it will talk about, if you're defining x like this way and summing up. So suppose k number of what we call it k number of success are there, that k number of student getting A, and rest n minus k will not get A. So simply what kind of nature x will have? X will talk about number of students that get A, grade A, and we can further say that the number of successes, x contains number of successes in n trial. So what would be that number of successes? It would be definitely less than equal to k, and n less than equal to n, and hence we can say that x is what? It is a binomial random variable. It is talking about k success out of n trial, binomial random variable. So we can easily calculate the expectation of x. What would be expectation of x? And same, this binomial random variable is actually also talking about number of students that get grade a. Same thing it is talking. Okay, so if you are trying to calculate expectation of x, and so expectation of x easily you can calculate as a summation of expectation of xi, because due to linearly independent nature, and we know that each one is having probability, expectation is 1 by 3, and how many students are there? 300 students. So simply expectation of x would be 300 times 1 by 3. So cancel it out, 3 will cancel here, finally you will get 100. So 100 is the 100. So you, out of 300, 100 a student will get grade A. So that is the answer. Another problem, similar kind of problem, hat problem. So suppose there are n number of people, they throw their hats in box. Okay, they put in box, then each one picks one hat at random. Then what is the expected value of x? That means the number of people that get back their on hat. What would be that? So here we have to solve this problem again, this hat problem. So for this again we will introduce Bernoulli random variable. For the ith person, we introduce a random variable xi that takes the value 1 if the person selected his or her on head. Okay, and that random variable is taking value 0 if that person failed to select their on head. Okay, so simply xi is a Bernoulli random variable, we can say that. Since, and now further we will calculate probability of picking on head, that means xi equal to 1. So xi will take taking two value, either it will take 0 or it will take 1. If there is a success it is 1, if there is a failure it is 0. So what is the probability of success? Probability of success, that means equally likely situation is n people are there, or each people are equally likely, they are picking the what had at random. That means if nothing is mentioned, by default it would be equally likely situation, and hence probability of success would be what? 1 by n, and probability of failure would be what? 1 minus 1 by n. So this is the, this simply you can say that it is p, a small p, that probability of success, and this one is 1 minus p, probability of failure. Now if you try to calculate what expectation of each Bernoulli random variable xi, again apply the formula of expectation, and from there you will see that expectation of a Bernoulli random variable happens to be probability of success. That's why I used to call it probability of success. So expectation of this xi is what? 1 by n. Now once we are having this, but our main question is that we have to find the expected value of x, that how many numbers of people that get back their on hat. So that for that perspective we are defining a sum of these n number of Bernoulli random variable, and this sum would be what? Again we can call it, it is a binomial random variable. In nature, binomial random variable would come. Okay, and now what you do, if you are trying to find expectation of x, and due to independency we will see that it is sum of n number of expectations of those Bernoulli random variable. So that's way n times, and each Bernoulli random variable is having expectation 1 by n. So in average, uh, what uh, uh, what is the expected number? That in average one person will get one head. Simply answer of this one person will get, in average, in average expectation and average both are same, in average one person will get one head. It is not in totality you can say that, in average. Now we are going further. I will here introduce conditional probability mass function. So it is implied from conditional probability, you can say that. So in a probabilistic model, if a certain event has occurred, that means we have already seen the happening of a, then we can talk about conditional probability mass function of the possible values of a random variable that has been conditioned by the observed event a. That how we define it? So we define conditional probability mass function of x given a. We are calling it given x given a. It is a function of x. So we define again with the help of this probability. Always we will define the corresponding probability mass function in the term of probability. That means simply express if it is function of x. So simply what we are saying that means p it is probability that x is taking value x given a, conditioned by a. Okay, and if you further try to look, I had mentioned that each value of the random variable, it defines an event in the sample space. So you can simply say that it is an event. It is an event. So we can talk about conditional probability perspective. We are saying that how much of this event, that means x equal to x, is happening within a, that we are talking about joint occurrence of event with a divided by total occurrence of event a. So this is the definition. Directly it is coming from the definition of probability, conditional probability. It is directly coming from the definition of conditional probability. Simply I would like to say that if you further try to see it, try to talk about this kind of things, this event, this joint event, that means x is observing x jointly with a, then the event are disjoint for each different value of x, and then if you take their union, then their union will give back a. So in that sense we can say that this kind of event is introducing partition of a. So one more thing I had discussed, that if you are taking a discrete random variable, then if you try to map back to sample space, then that one is introducing one kind of partition. So discrete random variable is taking value in discrete fashion. That means you can say that x1, x2, x3, like xn. You can say that n number of, suppose discrete random variable is taking n number of variable. So in that perspective, x1 will map to, you can talk like this way, sample, this one is the sample as x1 is the image of a1, x2 will give a pre-image a2, second member of the partition. Likewise xn will give an. And here partition, if discrete random variable always introduce partition. So with respect to that scenario, if you are having a partition of a sample space, this one is the sample space, and I had already mentioned that the partition of sample space also introduced the partition of what the event, particular event. So event, we are having event a, so we can say that this partition also introduces partition within the event. So due to that, if you try to calculate probability of a, so you can say that the probability of a would be what, this summation of all those, the probability of joint occurrence of x with a, and sum over all x. Then this directly, it is very much related with partition approach that I had already discussed that. So if you take summation over all x, then it will what if you say here you do summation over all x, that means vary for all x, then what it becomes, so it simply it will be converted into probability of a, and in denominator we are having probability of a, both will cancel out, and hence we can say that in total, if you vary all x, then this conditional probability is satisfying joint marginalization or normal condition. That means total probability would be equal to 1 if you sum over all x. So that's why this conditional probability mass function, it is a legitimate or genuine probability mass function. It will satisfy all the properties of being a probability mass function. What are those property? First property was being positivity. That means if you're defining any probability or joint probability mass function, that must satisfy this condition, that for every x it must be greater than equal to 0. It can't be negative. Second property was you are finding the probability of an event like this way, and same. And third property I am talking about marginalization. That means if you sum uh, the corresponding probability mass function or conditional probability mass function over all value of x, then that sum would be equal to 1. This one we are calling it normalization property. So this conditional probability is satisfying all these three property, and hence we can claim that this conditional probability mass function is a legitimate probability mass function. So now I'm taking one example. We consider an experiment of rolling a dice, and a be the event that roll is an even number. So this we have already observed. Roll is an even number. This a is the event. Now we are defining here a random variable x it is talking about the roll of dice, the roll of dice. So x will, if you don't focus over here, then x will take 6 value. X will take 1 2 3 4 5 6. Okay, but if you observing a, and if you are not observing a, from that perspective the distribution of x would be what, 1 by 6. It is in uniform distribution, it would be 1 by 6. For each value of x, probability would be 1 by 6. So this is the distribution for this random variable. Okay, it is uniform random variable. But suppose if you have already observed a, then your distribution will be changed. What would be that? That we will call it conditional distribution. That means what is the probability, conditional probability mass function for x given a? So again we will talk about that probability that x is taking value x given a. Given a means our new sample space is talking about that even row. That means what are the even row? So a is talking about what kind of event outcome a contains. A contains 2 4 6 even numbers, even faces. So and hence we can say that joint occurrence of x with a, it would be what, um, it would be any of these three. So how many we observe? Three, and hence we can say that conditional probability mass function, it would be 1 by 3. So if you are taking any one x, so all are what, equally likely. There is no situation that one is repetitive in nature. So conditional probability mass function would be 1 by 3 for x equal to 2, 4 or 6. So in that sense also, how much of 2 is happening, you can say, you can calculate from the conditional probability itself how much of 2 is happening in a, how much that how much 2, 1 is not happening, 1 is not an even number. So definitely for that probability mass function would be 0. 2 is present in this event a, so that's why probability of x equal to 2, it would be 1 by 3. 3 is also not present here in this a, so that's why probability mass function for the 3 would be 0, and 4 is present, so that's why probability mass function for 4, it would be 1 by 3, and 5 is also not present, so probability mass function would be 0. 6 is present, so that's why probability mass function would be 1 by 3. So that is the way to calculate conditional probability mass function. Here we are introducing conditioning by some observed event or some observed value of the random variable. Now, how we can visualize this same conditional probability? So visualization, I have taken it here like this way. So to obtain conditional probability mass function, we add the probabilities of the outcome that give rise to x equal to x, and that x is coming from that observed event A. And we further what we do? Further we do normalization by dividing probability of A. So like this way. So suppose we are having a event a, this we have already observed, and if you are willing to calculate x equal to what is the probability mass function for x equal to x, so we have to go back for this x, we have to go back into sample space, and we will see that what are the intersection of pre-images of x with a. So what are the intersections? So this is the intersection. So this probability we have to, so definitely it will have many outcomes, so we have to find the all the probabilities, we have to sum up all the probability, and probability of all these outcome is what, this with this side, this is the probability of all these outcome. If you are taking another uh, value of observed value of random variable x dash, so definitely x dash will have pre-image in sample space, and you have to look into sample space that pre-image, how much intersection, how much that pre-image is happening within a, so this much is happening, so this will give our value of probability mass function for x dash. So this one, you can see that area is very small, so that's where this height is very small, and this one is very big. So this is what it is, a probability mass function, conditional probability mass function, geometrical visualization.